All right, hey guys. So we're gonna be covering lesson 8. It's honestly just a lot of going through hypothesis testing, confidence intervals again. Um, yeah, no, there's just a lot of taking old information and kind of rehashing it to serve a lot more advanced purposes now. So without further ado, let's get right in. So, going way back to when we first introduced the hypothesis testing, there's always been the 5 steps for really how you do it. So the first is that you always have to like check your assumptions and then write out your null and alternative hypotheses. And then from that, you calculate the test statistic. Using that, you then determine the p-value. Based off the p-value, normally if it's less than 0.05, that really determines what your decision is going to be, and then you just end up stating that in a real world conclusion of there's not enough evidence to reject the null, or there is enough evidence to reject the null, stuff like that. It's stuff that you guys have been doing for a good while now. So with that, we kind of have a rule of sample proportions. So we're just like going into sample proportions for using it. So basically, you can only use it when these two assumptions are met, these two requirements. Basically, n times p, so the sample size times the proportion, has to be greater than or equal to 10. And n times 1 minus the proportion also has to be greater than or equal to 10. So if that's true, they can move forward. If it's not true, then you just can't do it. So if it's true, then the distribution of sample proportions will be approximately normally distributed, and mu will equal the proportion, and the standard deviation will be that equation there. That's not very pretty to look at. Basically, it's the square root of p times 1 minus p divided by n. So going back, confidence interval for sample proportions. So the way you calculate it, well, at least the way you use it, like shorthand, the way they have to write it out, the way that you're really going to be tested on, it uses this equation where p hat plus or minus the z multiplier times the square root of what we just had in the last one. It's pretty much, just using the standard deviation equation, plugging it in right there. So where p has the point estimate and the z multiplier is based on your confidence level, which I included a nice handy little table here. So this is not all inclusive. This is not every single one you're going to see, but this is generally the most common confidence levels you're probably going to see, with most of them being either 95. Most of this got to be 95, but so basically, if it's asking for a 90% confidence level, then the z multiplier is just going to be 1.645. If it's a 95% confidence level, that's going to be 1.96. Usually, you can just round that up to 2. Makes it a lot easier to remember. I'd recommend memorizing them, but I wouldn't put in like a ton of effort into memorizing them. I think just as you do the homework problems, as you get like a little bit more familiar with it, you should just be remembering them as you go. And if it's not on this table, you're probably going to be asked to calculate it. You're not going to be asked, you're not just going to be asked to know it off the top of your head. So when it comes to hypothesis testing for proportion, first you have to make sure that you meet the basic requirements, which I went over earlier, that n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. So then from that, you kind of write your null and alternative hypotheses. So this table should look very familiar. It's basically all of hypothesis testing really summarized into one tiny little bit. So if the question is the proportion different from the null, then the null is going to say no, it's the same. The alternative is going to say it's not equal to. And so then you'd be doing a two-tailed test. It was asking is the proportion greater than the null. So the null's, of course, is always going to remain the constant. So it's going to say it's equal to. It's going to say p is greater than P null, and you got to be doing a right tail test. And then if it's less than, same thing with a less than sign and a left tail test. So once you get through all that, you calculate the test statistic. So here's this nice equation. It's basically, again, you just kind of got the standard error here, and you've got the sample proportion minus the null over just the standard deviation. It's stuff that you have seen before, but just in different nomenclature. So I would recommend writing down any equations you aren't really familiar with. I think you can kind of like look at them and figure stuff out, but also just know you're never going to be asked like the theory behind them. You're never going to be asked like derive one of these equations or anything like that. So you don't really need to know like where these equations come from. Just know how to use them. And then just finishing it off based on that, you determine the p-value, you make a decision, and you stay in the real world conclusion. You're going through the same 5 things. Just I'm also just trying to highlight the stuff that changes, because this stuff it will never really change. However, the other stuff there's a lot more. All right, so central limit theorem. This is really dealing more with means. So if you have a sample size of at least 30, then the distribution of means will always kind of be like normally distributed, regardless of the shape of the population. And so means always going to be equal to mu, and the standard deviation is going to be equal to the equation I have just right over here of, standard error divided by the square root of n. So when it's coming to confidence interval for a mean, you guys are probably going to see a lot of the same stuff just repeated. It's kind of like mean, portion, different by very little amounts. So when you're calculating it by hand, it's going to be the point estimate, which we've seen before, plus or minus the multiplier times standard error. And so for the multiplier, you might see it a few different ways. It's generally going to be written as a T star. However, sometimes you'll see it as Z star. But just generally know it will be Z star. And it's just, X bar, which is the point estimate plus or minus the multiplier here times the standard error. So for computing the necessary sample size for a population mean, it's something they might ask you to do. It's got this nice little equation here. If you wanted, you could kind of take out the square root for each of them and then just square it at the end. So the z squared here is basically the given value. It's the x bar. It's all other stuff. The little o here is standard deviation, and then the e is just the margin of error. So really, it's just plug and chug to find the sample size. Most of the time, they're going to be giving you all the information. So with that, we kind of go into the hypothesis testing for a mean. I wrote out the table again. I'm not sure why the top there didn't show up. Kind of weird, but it should just say is the mean greater than and is the mean less than, or right tailed and left tailed respectively. So when you're checking your necessary assumptions and everything, basically you just have to know that the data has to be quantitative and has to be randomly sampled from a population that is normally distributed. So you have to have n at least 30 or greater, and has to be randomly, the data has to be come by a random method and everything like that. So it's all the stuff that you've really been taught before, just like being compiled into one. So then paired means, you're basically adding this little d into the equation. You might see it as a subscript. It could be d as itself. You kind of see here you've got d, and then here you got d as a subscript. And T star is the multiplier. Basically, it's supposed to be degrees of freedom, which I think you guys have probably heard. Get ready, you're going to be hearing about it a lot. Personally, I think it's like the worst name thing ever. I just think it's so annoying to be calling it like degrees of freedom.
So I have a question on that. So we see the T star listed in places like this. And it seems like sometimes we're calculating a t-score, which would be something like a z-score, except for a little bit different. And then sometimes it's this degrees of freedom. And I'm kind of confused as to when to use degrees of freedom versus when to use the t-score we calculated before. They're different things, right?
Yeah, they are different. So basically, the T multiplier that you calculated before, it is different between whether it's a single mean or whether it's paired means. If it's paired means, then you're always going to have to use the degrees of freedom. If it's the single mean, then you're going to just be, using the other one that you calculated.
Okay, so we only use that t, the df minus n minus one if it's a paired mean. Is that
Yeah.
right? Okay.
Yeah. All right. So when you're checking for assumptions for the paired means, whether the requirements for using it. So the data has to be paired. The difference between the two groups must be normally distributed, or the sample size must be at least 30. If it doesn't meet these requirements, then they can't. So when you're calculating the test statistic for paired means, you got this nice jumbled mess of an equation, but it's really just the same thing that you've seen before, just with like slightly different, variables that are being used, but they're supposed to mean the same thing. So the D here is basically the exact same thing as the X bar, except it's just the mean paired difference. So think of it going back to the difference in means where it's M1 minus M2. That's what you're plugging in there. The mu with a subset of D is just the hypothesized, so it's the null value. Then you're just plugging that in, divided by the standard error again. So that's basically all it is.
So where are we mainly using that test statistic right there that you were showing? That's going to plug into what formula after you get that test statistic?
That's what you'd be plugging into the paired means one. So it's basically what's happening is the degrees of freedom are saying that with degrees of freedom being n minus 1, then this can take place. But if your degrees of freedom is different, then your t-score is also going to be different. That's basically what this equation is saying.
I don't understand what you just said at all there. Sorry.
So as your sample size changes, so does your degrees of freedom.
Right.
So, the larger your sample size, the larger your degrees of freedom, all that stuff. But then that also is going to affect the standard deviation, and it's also going to affect the t-score. So basically what it's saying is, so long as the degrees of freedom is equal to this n minus 1, you can use this equation. If it's something different, which it shouldn't be, then you can't use the equation.
You can't use which equation? So go back a couple screens there that you were at, right?
Yeah, you can't use this equation.
Okay.
It's basically like another requirement where degrees of freedom has to equal n minus 1. It's just kind of more of an unspoken requirement, since most of the time that is already met, and degrees of freedom is normally rather easy to calculate since you're just doing the sample size minus 1.
Okay. So the confidence. So what we would be doing on a normal basis is what I have for the confidence intervals for paired means, and the Word document that we have it doesn't look like that to me for some reason. So if I do the confidence for paired means, I see it being where the confidence interval, it is xd plus or minus t star, and then okay, that is the same thing. So t star, what is the t star there then? Is that going to be the n minus 1, or is that going to be a different number that's based on the test statistic, which is a little bit more complicated to get to?
It's based on the test statistic that you calculate here. It is the test statistic multiplier. So you calculate using all that stuff, and you plug it into this. And I know like the equations always appear a little bit differently. It depends on like who's writing the textbook, who's presenting the data and everything.
Mm-hmm.
You can get them in numerous different ways. So long as you recognize that D bar or X bar with like a subscript of D or something like that, it all means the same thing. It's just written with a little bit different nomenclature.
Can I show you my screen for a second so I can understand what I'm saying? Because I think I'm just not computing this. I don't know if it's possible or not.
Can we just do that at the end, and then I'll get to it? Because
okay.
we just got a little bit more to get through. I've just got to do the review now, and then
Okay.
so yeah, this is the first question. It's basically just asking you about whether or not you can conduct a hypothesis test given the information. So I'll give you guys a little bit of time to work on this, and then you can just put your answers in the chat box. All right. I think some of you guys are having a little bit of confusion between hypothesis test and confidence interval. So for if it was a confidence interval, you would not be able to because you would need to have it would be the 8 here that in the dog times whatever, and you wouldn't get 10. However, for this case, you could use it because you'd be using sample size of 30 times the proportion of 0.5, and you'd be getting 15. And you'd be getting the same answer for both cases, which is above 10. So you can use a hypothesis test in this. However, you cannot use a confidence interval. Sorry, I kind of threw a curveball at you guys, but it's just something good to know because this is an exact question that was pulled off of a quiz. I just altered like a few little things. So you just have to remember the difference between hypothesis test and confidence interval. Hey, most of you guys always get the questions right, so I gotta do at least a little, spice things up a little bit, especially after the ref decided that that ball was playing the dog. All right, so review two. Given the table below, what sample size would be necessary to construct a 95% confidence interval with a margin of error of 5%? So you're given everything here. If you guys want, I can go back to the equations sheet so you guys can write it down. I imagine most of you probably already have it down, so just let me know and I'll give you guys a little bit of time to work on it. All right, guys, I'm just going to go over this one. It seems to be a slow one. So the correct answer is D. I just have the entire thing kind of written out right here. Although it doesn't look great. So that should be, sorry, that should be divided by. But basically, you just plug everything into the equation for finding sample size, which is this one right here. So the margin of error is just 0.05. Since it's a 95% confidence interval, you're just going to use a z multiplier of 1.96, and it's asking for that squared, which doesn't look good, and then it's just multiplied by the proportion, which back is 0.8 that you get from the non-alcoholic percent, and multiply that again by 1 minus 0.8, and you end up getting 245.862. But you always have to round up. Like, even if it's 0.1 or something, you always round up, because you can't say, you have to include an entire person. You can't say there's like just part of a person. So that's how you end up getting 246. And any questions? Just want to make sure people understand that, because I know these questions are pretty tricky, but I'm just trying to make sure you understand the content. Go back into this.
So basically, we're saying we don't know what the proportion is, so we're using the one that we know, which is the non-alcoholic. So it'd be 0.8 minus 1.8, because that's what we're targeting to meet that 80% threshold, right?
Yeah, what we're looking for is looking for how many, like how large of a sample size we need. So
Right.
yeah, to hit that threshold, we need to use the 80% that we got.
Yep. So if you'd asked for alcoholic, we would have used 0.2 instead of 0.8. But instead,
Yeah,
because it's non-alcoholic, you said.
yeah, and then you just have to remember from confidence intervals that the 0.95% confidence interval is approximate to 1.96 multiplier, or 2, and you just have to know that back to the equation, that the margin of error is just where you're going to plug other stuff in. So
Right. Cool.
on to review number 3. I think this is the last one. So given S equals 3.6362, what is the minimum sample size necessary to construct a 95% confidence interval with a margin of error of 0.5? All right, I'm seeing a little bit of confusion, so just go over it. You're looking for n, so when you're going back, I guess that should probably be more of, yeah, I probably should use a different, okay. First off, this is not my question. I took this directly from a quiz, so I'm not sure why they gave you S, but it's plugging into this equation here, which is just a rewritten one of the sample size equation. So it's just alter a little bit. It's just this. So I'm going to assume that yeah, I'm going to assume it's the standard deviation. Just so with that, you know, end up calculating it all the way out. That's supposed to say it's 14 point whatever squared, not 0.2. All other stuff, I don't understand why it doesn't have the squared. Then you end up getting 203.174. But then again, you have to always round up, so you end up getting 204. So sorry that this was a little confusing to you guys. I'll work on some of the questions a little bit more for the next reviews because I was pulling this ones directly off of old quizzes. So, so with that, we're done. This one's gonna be come back Sunday. If you really want, it's gonna be the same review. I'll probably just change the questions a little bit to make it a little bit more fair for you guys, but it's gonna be the same thing. This one's also gonna be uploaded to YouTube, and yeah.